Okay, good morning. Let's start the last session of this very nice symposium with this friendly group. And in the last session, we have 3 works to be presented. When we start with an invite talk, loose mode resonance based on sensors with phase matching layers, and it will be presented by Ignacio Del Villar Fernández. Professor Ignacio Del Villar finished the Ph.D. in 2006 and works as an associate professor since 2008 in the Public University of Navarra, where he is a lecturer on subjects in the domain of instrumentation, electronics, and communications. Regarding research, he owns 3 6-year terms positively evaluate and is a co-author of 125 articles published in international journals and so many other good indicators. And please, Professor Ignacio.
Thank you very much. Okay, thanks, Professor. Good morning to everybody. Good morning to everybody. Well, as Professor Jan said, the title of this presentation is Lossy Mode Resonance-Based Sensors with Phase Matching Layers. Well, first of all, I'm going to show you some fundamentals, some basics on lossy mode resonances, which is a topic we have been working during the last 15 years, more or less. Light can be guided through an optical fiber like this one. If we don't modify the fiber, if we don't modify the fiber, the transmission spectrum here is similar to the transmission spectrum we get in the output. By removing the coating and the deposition of a thin film, we generate a resonance in the output, you can see here, that depends on the surrounding refractive index and the thin film tube. The conditions for LMR are different from surface plasmon resonance. Nowadays, I think that there are more people aware of this, but in the past there was some confusion between both phenomena. And there is a publication from 1997 where we can differentiate the conditions in terms of permittivity of the thin film, the real part, the imaginary part. We can summarize these rules by saying that the LMR conditions obey to materials that are rather dielectric, metal oxides, polymers, and SPRs are generated better with metals, with silver, gold, typically. Here is well, a video we developed at the beginning showing the wavelength shift of the resonances as we deposit a titanium thin film. During the first steps, as we deposit the thin film, we can see the first LMR, then the second one, and the wavelength shift of the resonances is a slowdown. So as we increase the thickness, the wavelength shifts lower. This is related to sensitivity, and we will explain later that sensitivity is related to the order of the LMR. It is better to use first order LMR. This video can be summarized in these graphs. Here we plot as a function of thickness and wavelength the transmission. And so each line in this direction is the transmission spectrum. So what we can observe here is that this is the first LMR, this is the second, third, fourth. So the first one is much steeper than the second one, the third. And in addition, this is done with titanium dioxide with refractive index around 1.9. If we compare a thin film of high refractive index with a thin film of lower, Here, the wavelength shift is lower than here. So it is better to use high refractive index materials. Here is the relation between theory and experiments, and it is important to highlight that with a simple simulation method that considers ray optics, we can obtain quite accurate results. And this is because we are working with cladding remote multimode fiber, which is a thick waveguide. Probably with single mode structures, we need more advanced software. Regarding the development of LMR-based device applications, we can say that one of the applications is optical filters. Obviously, the transmission bands, the tips we have seen there correspond to optical filters, but these filters are rather broad, so the main applications are sensors. I will differentiate two types of sensors. The first one is obtained when there is a variable thin film refractive index or thin film thickness. Then we get chemical sensors, biosensors, gas sensors that will monitor a parameter depending on how the thickness of the nanocoating or the refractive index is affected. If we pay attention to the external refractive index, then we develop refractometers. But refractometers is not high interesting topic because there are many commercial devices and it is difficult to counteract with them, though our refractometers reach very low limit of detection of around 10 to -6. And in addition, with refractometers, we can, with optical refractometers, we can monitor not only a single wavelength but different wavelengths. So the rules for optimizations of these sensors were summarized in 2012. Here is a wide set of rules. And if you can see this, the main parameters to consider are the coating thickness, refractive index, and surrounding medium refractive index. And by increasing the parameters, we get higher sensitivity. More recently, there has been more research on the topic, and the previous rules have been better specified to boost sensitivity. And the first rule that we can consider is that the refractive index of the waveguide, of the substrate, must be very similar to the surrounding medium. If we approach both parameters, we get very sensitive sensors. For instance, with side-top fiber, with refractive index very similar to water, the sensitivity is increased a lot. To operate at long wavelengths, and with the first order LMR we observed previously. The thin film refractive index as high as possible, though there is a limit, it saturates for very high values. And all this agrees with analytical equations obtained by Sabeljev in this journal and by the group of Kiwan more recently in this other work. Here is, for the first time, the equations for T and Tm, analytical equations for sensitivity. And it is interesting to observe something that was observed empirically during the last years, that the sensitivity is proportional to the square of the wavelength. In addition, the other parameter to consider is the cutoff thickness of the lossy mode resonance. The thickness for generating the LMR rules also the sensitivity. That is why with lower order LMRs obtained with thinner coatings, we get a better sensitivity. So these two parameters are fundamental. And also, as I said to you before, the thin film refractive index as high as possible, but it is not so easy to observe it here. If we solve these equations and plot them as a function of N2, we observe that there is a high growth as we increase the thin film, but later it saturates. But these equations only consider the sensitivity. If we focus also on the full width at half maximum, then we obtain the figure of merit. And the figure of merit gives more information than the sensitivity. The figure of merit is the ratio between sensitivity and full width half maximum, and it accounts for sensitivity and how narrow the resonance is, and this is related to accuracy. So we must boost both parameters, sensitivity as high as possible, full width half maximum as low as possible. And it has been observed, not with these analytical equations, with more advanced equations, that the full width half maximum is decreased when we operate with single mode structures. So that is why, for instance, we will see now some results with D-shaped fiber sensors, which are single mode structures. We get very good results. Here I show some examples. The femtomolar detection of IgG with a D-shaped fiber sensor. This is the calibration curve obeying to 4 different sensors. This is the sensorgram, where we can see the wavelength shift in serum. And here is what I was saying before. If we compare D-shaped fiber single mode with cladding removed structures, which are multi-mode, the wavelength shift in the biosensor is much higher than in the other case. So this work is probably the only one or one of the few works where we compare single mode structure with multi-mode structures. And regeneration. The sensor could be regenerated several times under the same concentration in SDS solution. Well, here I show some other examples of biosensors. In this work, we could detect D-dimer at concentrations below the threshold for venous thromboembolic disease. Tau protein is a very important molecule for Alzheimer's disease, and we could detect nanogram per milliliter in serum. So it's close to the range of Alzheimer's disease. Here we have an example of a very small molecule, perfluorotonic acid, less than 1 kilodalton. So the challenge here is to detect a small size molecule. And finally, I would like to show you a work on regeneration. 2 slides before I showed regeneration, but here the merit is to use a covalent immobilization method and to regenerate the sensor several times and under different concentrations. With hydrochloric acid, we could regenerate the sensor, and depending on the time we spend in hydrochloric acid, this concentration is adequate for higher concentrations of the target analyte. So the target analyte, the concentration or the time of hydrochloric acid depends on the concentration of the target analyte. And one interesting work I would like to show you about chemical sensors, because with cladding remote multi-mode fiber, I don't say that it is a bad structure. So the only thing I say is that the performance with single mode is better, but it is easier to manage, is less expensive. So there are many groups that use it. And here is one example by the group of Gupta, where he deposited molecular imprinted polymers. Here's a very interesting work, because here in this graph, he compares the performance, this is blue, without molecular imprinted polymer, and the sensor detects cortisol, cortisones, progesterones, many molecules under the same wavelength shift. So it's sensitive to everything, we could say. And with the molecular imprinted polymer, the sensitivity is enhanced a lot, and the selectivity also. So this is the merit for this work. And he reaches in this calibration curve limit of detection of femtogram per milliliter. Other properties of, because I could show also there are also gas sensors, humidity sensors, but well, this is just a few examples. Other properties of LMRs and SPRs can be observed here. One interesting question is the angle of incidence. LMRs are typically obtained with angles of incidence approaching 90 degrees. Whereas SPRs, the typical range is 40 to 70 degrees. So the best setup is Kretschmann configuration for SPRs. So here we can see the typical setup for SPR, whereas for lossy mode resonances, we typically impinge laterally in a waveguide, in a planar waveguide, or with optical fiber, indeed, we are impinging laterally compared to the perpendicular plane, to the thin film. Other parameters are the polarization, LMRs I obtained with T and TM, SPRs only with TM, sorry. Spectral tuning, as you have seen in the video, it is quite easy as a function of thickness to move the LMRs in the wavelength spectrum, and we can get several resonances. So multi-parameter sensing is open thanks to this property. Can we modify the best angle of incidence for LMRs? Because as we have seen, they are obtained with 90 degrees, more or less. Well, in a work published by José Javier Imas in optical laser technology recently, he has explored the utilization of intermediate layer between the thin film and the waveguide. So the idea is this setup. In a Cressman configuration, we have the optical pins, we impinge the light, and we have the thin film, but between the waveguide and the thin film, we have a matching layer, an intermediate layer. So here, he has explored the effect of using this matching layer when we deposit titanium, and both experimentally and with simulation. And we observe that the resonance is more visible around 70 degrees. So we have moved the angle of incidence for exciting the lossy mode resonance. And this has the implication that sensors are more sensitive when we approach the critical angle. So this is the advantage of this approach. So first of all, I will focus on these phase matching layers. We can call it phase matching layers, intermediate layers. There are different ways to talk about that. First of all, dielectric is the thing I am going to show you. This was a work published a few years ago by Dairon Armas. He used this setup, a glass waveguide deposited with a titanium dioxide, and the intermediate layer is silica. So by simulations, we observe as a function of thickness that of the thickness of the silica layer, that the resonance shifting wavelength, and there is some thickness where these resonances are more visible, here and here. So in one case for T and TM, in one case around 300 nanometer, in the other 200. So the best thing here is that we improve the visibility of the resonances, and this was confirmed here experimentally, that the resonance is shifted to shorter wavelengths, and there is a maximum of visibility, and later it fades, similarly to the simulations. It is interesting to observe that the good point is the visibility, so the full width at half maximum could be improved, but the sensitivity also decreases. So the bad thing in this work is that the full width at half maximum decreases, but also the sensitivity, so in the end the finger of merit is quite similar. I must point out that this non-improvement is due to the accuracy of the thin film. If we improve the quality of the thin film, we could improve the figure of merit. Here I show this work because it's worth mentioning. This was by a Chinese group, the Dai et al. In biosensors and bioelectronics, and they use the same structure you see here. So they obtain the same wavelength shift. The intermediate layer here is magnesium fluoride, and they could detect PSA, which is a biomarker for prostate cancer. I think this work is quite interesting because they experiment with human patients, and they compare their data with electrochemiluminescence, which is a more an older technique which more works on it, and the results they get, they are quite similar. They compare the results by electrochemiluminescence with TE and TM resonances. And here is the graphs with by tracking positive and negative patients, and there is a good agreement again with the electrochemiluminescent technique. Now I will focus on the metallic intermediate layer, which is the other possibility. We have deposited a dielectric with a metallic layer. This is the setup we have. And we have a cover slip. This is the waveguide, the thin film tin dioxide, and we use gold for this example. We explore different gold thicknesses. So here, with just 15 seconds, we get a very narrow thickness of gold. This is nearly visible. Here, 12 nanometer, 17, 26, 35, 45. And we compare the results by using all these structures. So the evolution of the transmission spectrum as a function of gold thickness is shown here. Here there is no gold thickness, and we observe the TE band, the TM band, and as a function of wavelength it fades. This is a typical problem, especially in planar waveguides, that at longer wavelengths it is quite often the resonance is lost. However, with gold layer, the position of the bands is exchanged. This is quite surprising. We have analyzed with modal analysis. I won't focus on that now. And with thicker gold layers, we observe that the TE band fades and the TM also, but for a thicker coating. So what is the most interesting part in this metallic intermediate layer? Here I show well, experimental and theoretical transmission spectrum with an optimum around 20 nanometer, and you can see here that the deepest band is here, similar to the simulation results. So this is a quite important thing. Probably you don't see great improvement in terms of the width of the resonance, but obtaining a deeper resonance, we will see later, that has some advantages. In terms of refractive index analysis, the deeper case is observed here as a function of refractive index. There is a wavelength shift to longer wavelengths, and the signal is quite stable. Here we analyze the noise. However, with this resonance that is less deep, the signal is more noisy. So in this table, we summarize the parameters. There is not a great improvement in terms of figure of merit with 12 nanometers, 17 and 35. We get 18, 21, 20. It is better the thickness of around 20 nanometer, but the improvement is not very high. But the standard deviation is improved by a factor of 2 compared with this sensor, and by a factor of nearly 10 with the other one. So the important thing here is that with a metallic intermediate layer we can tune the depth of the LMR. Going back to the idea of the incidence angle, we decided to explore the metallic intermediate layer in Kretschmann configuration. This is the setup we use with the optical prims, the gold layer, the tin dioxide layer. And with simulations, we can observe that the sensitivity increases a lot as a function of the angle as we approach the critical angle, both for just the gold layer structure and for gold plus tin dioxide. Regarding the figure of merit, things are not so clear, but what is clear is that going to lower angle of incidence increases the figure of merit. And the case of the gold is in red here, and if we focus on the 30 nanometer or 40 nanometer approximately, we get even better results than with gold. And these results could be improved because here the tin dioxide layer we consider losses, but if we reduce losses, according to simulations, we could increase the figure of merit. Here are some experimental results. We explore structures with gold plus tin dioxide, gold with different thickness, And in terms of sensitivity, again, we see the increase of the sensitivity for lower angle of incidence. And in terms of figure of merit, the case of 36 nanometers was the best structure. So some conclusions, well, lossy mode resonances can be used in many applications: refractometers, biosensors, chemical sensors, humidity sensors, gas and volatile organic compound sensors. There are two main configurations: optical fiber and planar waveguide. And if we use an intermediate layer, the degrees of freedom increases and the resonant width is reduced, but the sensitivity decreases, so we must improve that in terms of figure of merit. The LMR, this is perhaps the most interesting point, can be tuned and improve the signal to noise ratio for biosensing applications. And we have explored this with dielectric and metallic intermediate layers. So the intermediate layer affects the operating angle of incidence, and if we approach to the critical angle, we could increase the sensitivity. So this line is where we are working now, and we should improve this. Okay, so and that's all. Thanks for your attention. I will show you a photograph of our group and some acknowledgement.
Thank you, Professor. We have time for questions. If no, I have. Okay, can you say some words about the cross-correlation between the signal of interest and temperature? And if yes, how do you compensate the temperature in the final results?
This is the cross-sensitivity to temperature is one of the most difficult questions in many sensors. This sensor doesn't have auto-regulation. I mean, for instance, tilted fiber Bragg ratings with the Bragg peak, you can detect temperature. So you need the idea is with biosensors, we typically use Peltier cells to regulate the temperature, and you achieve with a not expensive structure a degree of control that is acceptable, and in each experiment we monitor the temperature. But in order in a system to self-regulate, we would need, here I haven't shown, but you can use dual resonance LMR sensors. So in that case, one could be used for temperature, the other for the parameter to detect. And we have done a couple of works on that. Yeah. So.
Any other question? Okay, in this case, let's thank the speaker again.